Hello, everybody, and welcome to this quick Quake briefing hosted by the Northern California Regional Chapter of the Earthquake Engineering Research Institute. My name is Elizabeth Angel. I'm EERI's Communications and Program Manager. I'm glad to welcome you today. And for those of you who aren't familiar with EERI, I just wanted to introduce briefly the work that we do. We are the leading nonprofit membership organization that is dedicated to connecting people working in a wide range of fields in the United States and globally to achieve earthquake resilience and risk reduction. And if you are not an EERI member, I'd like you to invite you to join us. Some of the benefits of membership are shown here, from our flagship scientific journal, Earthquake Spectra, to the newsletter, webinars like these, involvement in our conferences and meetings, and many more things. You can find out more on our website at the address shown here. So now I'm going to turn it over to Volkan Sevilgen, who's the president of EERI's Northern California chapter, to introduce the webinar.
Hi, everyone. I would like to welcome everyone to our chapters webinar series, Quake briefings. And I would like everyone to participate in the question and answer session. I will be asking most of the questions. And here to introduce the speakers, Bruce Mason is our chapter secretary and treasurer. Bruce?
Thank you, Volkan. As Volkan mentioned, I am the chapter secretary, and I welcome you to our briefing on the magnitude 6.8 earthquake that occurred in China 2 months ago. Our briefings are free. One of our goals is to encourage sharing of knowledge as well as the interaction of earthquake professionals worldwide. And the way we do that is by talking about recent earthquakes. All of our briefings are available on YouTube for future viewing. Now, as Elizabeth said, one of the benefits of being a member of EERI is you would get advance notice of our briefing program. But if you're not, you can still get on our mailing list. And how you do that is to send an email to the address shown there. Next slide, please. Okay, but before I get started, I want to mention our next briefing that's going to occur in December. This will deal with a magnitude 7 earthquake that occurred on Luzon Island in the Philippines. This earthquake occurred in July. The epicenter was about 250 miles north of the capital, Manila. This earthquake affected about 500,000 people and caused much damage. We are having 2 speakers from the Philippines. This will be our 6th and final briefing for this year, so you don't want to miss it. It will occur on December 1st. Stay tuned because our notifications will be going out soon. Now, on to today's briefing. On September 5th, a magnitude 6.8 earthquake struck central China. We're very excited about today's program because this earthquake did not occur on the Pacific Rim of Fire. It occurred towards the middle of China, near the Himalayan mountains. This earthquake caused some spectacular damage, and we're very excited because we will be hearing about 2 base isolated buildings that suffered damage from this earthquake. We have 2 speakers today. One will talk about the seismology of the region as well as the mechanism of this particular earthquake. And our second speaker will report on his personal observations of building damage from his reconnaissance shortly after the earthquake. Today's format is for a 60-minute program. Each of our speakers today will talk for 20 minutes. After our first speaker, we will have a question and answer period. And how you will ask questions is using the Q&A button that you see at the bottom of your screen. Press the button, type in your question, and then Volkan, behind the scenes, will compile the questions. He will come back and pose them to our first speaker. Then our second speaker will talk, and he will speak again on observed building damage. And again, we will have a second question and answer period after that. Now, we recognize that we might have more questions than time permits. So both of our speakers today have kindly given their email addresses, and they're shown here on the screen. So you can email them directly with your questions, and they will try to answer your questions in the coming days. I would now like to introduce our first speaker, Professor Zhigang Peng of the School of Earth and Atmospheric Sciences at the Georgia Institute of Technology in the United States. He will explain the seismology of the earthquake. Professor Peng, please proceed.
So as Bruce mentioned, that what I would like to do today, maybe in the next 15, 20 minutes, is to briefly give you an introduction of the event and perhaps show you some very preliminary result that has been, either published or submitted, right after the event. As you know, that this event just occurred about 2 months ago. However, we have already seen some, publications that either are in press or some of them are already coming out. In particular, actually I have two hats. I'm, a professor at Georgia Tech in Atlanta, Georgia, but I'm also currently serving as a deputy editor-in-chief of a new journal called Earthquake Research Advance. And the reason I mentioned this journal is because some of the work that I will be presenting today are coming from this journal. So with that, I think, Bruce already gave you a brief introduction. I will be brief about telling you a little bit about, where the event is. I don't know if hopefully you can see on the, this is correct, a zoom out version. Obviously this event occurred in China, but if you really want to look at the location, it actually occurred slightly on the southwest side of China. The location, of course, occurred in the province called Sichuan. And in case you don't know where Sichuan is, that's where people eat spicy food, and that's where panda lives. But the event, again, has a surface magnitude about 6.8 and moment magnitude about 6.6. On the right-hand side is, I don't know if you can see my mouse, but maybe I'll try turning to a highlighter. Hopefully you can see this. On the right-hand side is the intensity. As you can see, that intensity is elongated in the northeast and northwest, southeast direction, which is actually consistent with then it being occurred on a strike slip fault, which we'll talk about momentarily. The USGS pager estimate this event to be, sort of moderate in terms of damage and casualties. This is another zoom out kind of version of where the event is, and also the focal mechanisms. I'm sure some of you have seen this before, but it basically shows the style of faulting. And if you look at that, this is basically a very classical left lateral strike slip fault. And the epicenter would place it right on or very close to the this fault, which is called Xianshuihao fault. And I will have a few slides later to talk a little bit more about this fault. But for now, it is basically a very large and mature fault that is, within the eastern margin of the Tibet Plateau. And if you look at the date here, in addition to this event, there were several, actually up to about 20 events occur on this fault in the past few hundred years. And again, if I have time, I will briefly talk about some of them as well. To zoom out, again, if you're looking at what happened in the past 10 years or 15 years or so, many of you know that in 2008, the magnitude 7.9 Wenchuan earthquake occurred to the northeast direction. And of course, the Wenchuan earthquake is a thrust, while the most recent one is a strike slip event. This is, again, another kind of slightly different plot just to show you that, this fault, which is, again, called Xianshuihao fault, has multiple fault segments, and it's connected to the northwest with another fault. And of course, as it goes further south, it also turns its direction. I have another zooming version. So again, this is a study actually was published almost about 30 years ago. This shows clearly that the Xianshuihao fault is a major kind of, you can consider as a block boundary within Tibet Plateau. You can also looking at, this on the right-hand side shows the event that have occurred in this fault segment and the surrounding region in the past few hundred years. Of course, the historic earthquake actually can go back thousands of years, but one of the events that I'll probably talk about in the next few slides is this event that occurred in 1786. It has a moment magnitude of 7.8 or so, almost about one order of magnitude larger. And we believe that this event might be the last event that have ruptured on this fault segment. Well, since many of you are in California, so I figured that I probably would do like a comparison to show you the similarity and differences between, the San Andreas fault, which everybody knows, and then this Shanxi-He fault. But turns out that I was unable to find a map that shows the fault comparison. The only one I found, of course, is the comparison between the San Andreas and the North San Antonio fault. So I did a little bit of trick by taking this fault and scale a little bit. So it may not be scaled properly, but if you look, the Shanxi-He fault, is right in the central portion of it, and the total length of the fault is about 400 kilometers. But if you extend it again further to the west and also the south, the entire fault system is up to about 2,000 kilometers, which is going to be actually very similar to the entire San Andreas or the North San Antonio fault. So, I won't have time to talk about more, but the similarity and differences are, the top two are the, right lateral, while the Shanxi-He fault is left lateral. The sleep rate is for the Shanxi-He fault is slightly slower, but it's up to about 1 centimeter per year. I shouldn't say second; it should be year. Okay, and finally, as you know, that on the San Andreas fault, that we have a so-called creeping section, and turns out in certain portion of the Shanxi-He fault, the fault is also creeping as well. And last thing, just to highlight that that in many places that the fault looks pretty complicated. It has stepped overs, and sometimes they have conjugate fault, which I will talk about that in the next few slides as well. Well, final slide again, talk about regional tectonics. This is a very spectacular paper showing the GPS vectors. And of course, both plots have slightly different reference frame, but hopefully that give you a feeling is how the big picture, of course, is the Indian subcontinent is collide with the Eurasian plate and build up of the Himalayas. But in addition to that, the Tibetan plateau has east-west extension, and then as it goes here, it has a interesting curve, and of course, majority of the deformation and sleeve is accommodated by the Shanxi-He fault, and of course, further to the west is called Ganzi Yushu, and further to the south is the Anning-He and Zhimu-He fault. Again, this is basically showing that the general regional tectonics, which have you seen. If you go further south, this is the so-called Red River fault that extended further to the Indochina Peninsula. Well, I already mentioned about that, just to kind of refresh your memory again, that this is the fault plane. This is the fault, and of course, the event occurred near kind of the junction between the Shanxi-He fault and the Longmen fault, which hosts the 2008 Wenchuan. And of course, a few years later, there was also a magnitude 6.6 earthquake occur in 2013. If you look again at the recent history, the two events that occur close to the recent event is two magnitudes close to 6 events occur in 2014. But if you look further back in time, as I mentioned, that this is the number of events and historic events since 1700. And on the bottom shows, of course, the fault segment going from north west to southeast. So this section, which is near a region called Moshi, is where the most recent event occurred. Again, if you look back in time, that this segment was believed to be last ruptured in 1786. If you look at other section, you can see that events have slightly different magnitude. But generally speaking, the magnitude are in the range of magnitude 6 to 7. The largest one is probably about 7.8 or so. Well, I think it's worth to mention about this event because this is clearly the last major event to occur in this region. One of the most significant aspect of this 1786 event is that, of course, obviously the main shock is much larger, is 1 order of magnitude larger. But in addition to that, it triggers a massive landslide that temporarily blocked the nearby river, which is called Daduhe River. And of course, it built a dam. About 10 days later, there was a magnitude 7 aftershocks, and this aftershock apparently triggered the dam failure, and then the flood water went downstream and caused much more damages and casualties than the main shock itself. This was clearly documented in historic recordings, but also recently there was also a paper published on that as well. So fortunately, the event occurred 2 months ago, was much smaller. It triggers numerous small-scale landslide, but didn't trigger any major landslide that blocked the river. So just to show you that this is again a further zoom out version of the study region. The event occurred here, but if you look at in the past 20 years, what we found out, which is quite unique and interesting, is that since 1997, which actually was yesterday was the 20-year anniversary of that event. Since about 2 decades ago, there are several up to about 7 to 8 magnitude, bigger than 7 earthquake occur in this block, which is called Bayan Har block. Majority of them are strike steep, but we also have, again, the wind channel earthquake is thrust, and we also have normal faulting event as well. Almost all those events occur on or within this block. This again probably indicating something, what we typically call that as a short-term clustering behavior. So again, this is one more slide showing the historic recording. You can see that it appears in the last 2 decades or so, there's a significant increase of activities in this region. One last figure showing what I have published before the event is that this a recent paper published in 2018 highlighted this section, as the section that has a about 30 to 70% of having a magnitude 6.8 to 7 earthquake in the next few decades, and apparently, of course, this event occur in this section. Well, in the next few minutes, I will just briefly talk about some of the recent findings associated with this event. Like I said, many of the papers are showing up in this journal. I will probably not going to introduce all of them, and so I'll probably just highlight some of the main findings. And I think Professor Zhe Qu is going to talk more about damages, so I will skip that as well. So one of the things that people have found out, and this almost become like a routine process nowadays, is whenever you have a moderate to large earthquake, you can do quick analysis to find out where earthquake rupture is and which direction does it propagate. Normally, it takes about days or sometimes weeks for people to find out. But nowadays, using a technique called back projection, you can, in this case, for example, you can use a distant earthquake. In this case, we're using P-wave arrival using station in Europe, and use that as antenna to find out where the rupture is. And the result basically shows that it appears that the main shock started here, but it's predominantly propagating south to southeast direction. We can do one step further to utilize this information and come up with a preliminary but rapid estimation of intensity. And you can see that, of course, the intensity matches very nicely with the observed or inferred rupture propagation direction. If you compare that with the actual observed, peak ground velocities and also intensity, you find they actually match up pretty well. And keep in mind that both are using totally independent observation. Of course, using the this is the traditional way where you use the recorded ground acceleration, while in the previous case we're using seismic recording at thousands of kilometers away. In addition to that, people can also do what they call as finite fault modeling to infer on how much fault sleep have occurred. And here you probably see about 6 or 7 of those finite fault modeling. Each use slightly different result, but the main finding is that the main shock, of course, started at the depths of about 5 to 10 kilometers, roughly about 10 kilometers. And predominantly, it's propagating to the southeast, south-southeast direction. Some of the studies also indicating that maybe there is a conjugate fault that perhaps have been ruptured at the beginning of the main event as well. But the predominant feature are the same, which is consistent with the back projection result. So this is a relocated aftershock location provided by Professor Fang Lihua at CEA, China Earthquake Administration. And again, you can see that the aftershocks are pretty complicated, but if you look at the cross section, that they are mostly near vertical fault illuminated by aftershocks. And in the central portion, you can also kind of see that the aftershocks seem to be extended further in the conjugate direction, which is consistent with the rupture that perhaps there is a small conjugate rupture in this direction as well. Finally, let's look at the aftershocks, and you can see the main event is close to magnitude 7. It was followed by many aftershocks, thousands of them. If you look at statistics, you'll find that you can do what they call as armorial decay, and the aftershock decays with a slope close to a little bit more than 1, which suggests that so far it's a typical main shock and aftershock sequences. So I want to quickly summarize the main observation we have. Again, this event occurred along the Qianshui fault. The last time it broke, we believe, was in 1786, more than 200 years ago. So it's quite possible that the main shock may have only released part of the stress that accumulated since that time. And in addition to that, from what I can tell, that it is a typical main shock and aftershock sequence. There's no obvious foreshocks, even though some of my colleagues in Sichuan told me that a few days ago, before the main event, there seemed to be some small event occurring in the epicenter region. So that remained to be further studied. Now, the aftershock patterns seem to be pretty complicated, but they seem to be mostly occur. I didn't have time to explain. They seem to occur just outside of the main shock rupture region, and it may have indicated that a conjugate fault may have ruptured during the main event as well. And finally, like I mentioned, that there are several methods indicating that the main shock and is likely propagated predominantly to the south and southeast direction, and that may have implications on the subsequent damages to buildings, and also numerous small-scale landslides triggered after the main event. So I think I'm very close to finished. Again, like I said, I will just briefly, talk about the journal again, because several of the work that I presented will be showing up to this journal. And if you're interested to find more, you can search for the acronym EERI, which stands for Earthquake Research Advance. Finally, I just want to give a little bit of some acknowledgement and also references to people who have provided help or slides. And you can find additional information for the links at the bottom. So I guess with that, I will stop here and see if there's any questions.
Okay, thank you so much for your presentation. I'm always amazed when we get presentations from other parts of the world, the complexity and the higher seismicity versus California. It's really striking. Okay, what I would like to do now is turn control over to Volkan to pose questions about the presentations. Volkan, please proceed.
Thank you again for this very loaded and exciting presentation. One question came to my mind about the triggering of this event from the 2008 Sichuan earthquake, magnitude 7.9. Can you make some comments about whether or not this earthquake is in the vicinity of stress triggering zone or not? Let's go ahead.
Yes, I heard your question, Volkan. Yeah, and thought I have included one of the papers published right afterward by your colleague Toda and Stein, but I did not. If I remember correctly, that the Coulomb stress calculation indicating that right around in this section, which is the broad region of the Shan-Shui-Hao fault, there are small but positive Coulomb stress increases in that region.
Mm.
So one could potentially, saying that the fault may have, the winter earthquake may have promoted the occurrence of this event. But of course, as you know, that the question would be like, why to wait for another 15 years or so? Why
Right.
didn't it occur immediately, right? So that's $1 million question we remain to be found out. I would like to, maybe take this chance to just add one more things, which I already mentioned. That is, again, if you look at this plot, right, almost all of the magnitude, bigger than 7 even, in China, not all of them, but majority of them occur in Tibet Plateau, occur within this block. So clearly there's something going on here. And what we can use, again, Coulomb stress to explain event in the vicinity, for example, those two events are likely, trigger with each other, but some of the events are actually quite far from each other.
Yeah.
So that's something, I just wanted to point this out. So there's probably something else going on, which we don't know what's going on.
Microplate or something. You also mentioned there was another event between Sichuan and also this current event. I wonder if that also contributed to triggering of this new event. I forgot when was the
Yes.
origin for that.
Are you talking about the event occurring in 2014?
I believe so, yes.
Yes.
So between these two, yep.
Yes. And I believe that because even though those events are closer in time, only about 7 years, but their magnitude are smaller. So if I remember correctly, some also calculated the Coulomb stress changes, and again, there's very subtle but positive increase. As you know, that when the event happens, normally in the same direction in front of it, you normally would have a slight increase of shear stress, but the increase is relatively very, very tiny.
It's probably further away is because the distances are about, what I can see is about 150 kilometers. Yes.
Exactly. Yes.
It's quite
you're right.
distant. This is really fascinating. Bruce, do you have any questions?
Yes. In particular, I'm interested in knowing in a general sense, what is the population that's exposed? In other words, on this plateau, how many people live there?
Good question. And I wish I have a better map to show you, but if I remember correctly, this is the USGS estimated, fatality and also the economic loss. And in short, there are people living there, and I'm sure Professor Zhe Qu is going to show additional footages and images, but it's definitely not as populated as, let's say,
is it in the
capital of
millions?
Sichuan.
On the plateau, is it in the millions of people?
Oh, are you talking about the entire plateau?
Yes.
Oh, it's definitely more than millions of people.
So exposed to these numerous earthquakes. Okay.
Oh, yes, obviously, yes. So there are, up to about perhaps 10 million people living in the plateau or in the surrounding regions.
Okay.
So they are definitely exposed to those numerous earthquakes. But I was mostly talking about this event. Of course, this event is relatively small in terms of magnitude. So it wasn't.
One other question I have is it's kind of interesting. I'm always impressed, like the earthquake that occurred like 1786. You're able to come up with a magnitude. Is the records in China that accurate? I assume that's a back calculation from some intensity. So you have to have a damage descriptions. How far back does the records go in China? I mean, of course, United States, we go back 100 years, 200 years maybe. How about in China?
Well, that's a good question. And I don't know if I have a plot here. The record, of course, shows go back to about 1300. But as you know, that people have living there for thousands of years. And, I didn't have time to talk about, one of the plot, I've jumped back and forth, shows later in one of the studies, we're looking at that the number of events, you can look at here, we go back to about, almost 1500 years. And actually, I put a reference here. There's a catalog that you can go back to as long as 2000 year BC. But of course, as you know, that as you go further back in time, the record is not complete. And almost all those magnitude is estimated by intensity. And sometimes the magnitude may be overestimated or could be underestimated, depending on if you're not using the correct attenuation model.
Okay, so in these dynasties,
yeah.
So in these dynasties, then they wrote these things down enough to know what objects had fallen and things of this nature and where.
Yes,
that's really amazing. That's
absolutely.
Very good.
Yeah. So again, hopefully this could be something of use for is, as you know, that those earthquakes are normally on the recurrence time is on the order of about hundreds of years. Sometimes it could be thousands of years. So if you really want to study them, you have to look back in time. I wanted to show you one thing. You probably cannot read here. Of course, it's also in Chinese, but this is a document. This is like a tomb or evidence of showing that when the event happened, that this 10 days later there was a dam failure that killed up to about 100,000 people in the downstream. And people actually set up, and write it down, in of course in the history recording, but they also set up this, like as almost like a monument to document that this thing have happened in the past.
Very good. Vulcan, do you have other questions?
No, I think this has been a fantastic presentation, Zhigang, and I cannot thank you enough for this. You really touched on every aspect of this event, and I think we now have a much better understanding of this earthquake and how that part of China we are much familiar with the tectonics of that part of China. Thanks so much.
Okay, thank you so much for an excellent presentation. Okay, I would like to proceed to our next presentation. Our next presentation will be given by Professor Zhe Qu of the Institute of Engineering Mechanics at the China Earthquake Administration in Beijing, China. He will report on his personal observations from his reconnaissance work shortly after the earthquake. Please proceed.
Okay, thank you, Bruce. Thank you for the introduction. And my name is Zhe Qu from the Institute of Engineering Mechanics. And I'm very glad to have this chance to share some of my findings about the building damage in the recent Luding earthquake in China. And I will first overview the building damage in the region, and I will then quickly go through some of the damage to buildings of conventional structural systems like masonry and RC frame, and also non-structural damage. And then I will focus on the two base isolated buildings Bruce Mason just mentioned about. I believe this is the first time to observe such damage in base isolated building, at least in Chinese mainland. And here I show the same intensity map Professor Peng just showed us. And actually, my reconnaissance were concentrated in this area to the northeast of the epicenter, and which is centered by the town of Moxi, which is a tourist town. And we got to the town through this path, and this area is full of high mountains, and I think it's better to show you a video to see what it looked like. This is the road, the mountainous road we get into the region, and the landslide is extensive. And this road used to be a busy road when people go deep into the mountain to spend their holidays because it's very good view. But after the earthquake, it becomes somehow dangerous because of the landslides and the falling rocks. And let's see. And actually, in this earthquake, most of the fatalities and injuries was attributed to landslides. You can see this landslide here. And under the landslide, there is a village of more than 100 families. And in this kind of remote villages, most of the buildings or houses were built by this kind of unengineered, structural systems like the traditional timber frame. And you can see here the masonry, the stone masonry. But instead, because that kind of poorly constructed buildings are known to be very vulnerable to earthquakes, so our reconnaissance mainly focused on engineered structural systems for earthquake protection. And this is the region of our inspection. And especially we focused on the town of Moxi. And most of the buildings we inspected are located in the town of Moxi. And luckily enough, we have 4 ground motion records denoted as the little triangles here. And of special interest is the Moxi MX record because it's very close to our buildings. And I think it's helpful to first have a look at the characteristics of the ground motions. In Moxi, by the Moxi record, we have a very high PGA, peak ground acceleration. It is over 0.4 G. And the more extraordinary is the very large PGV, which exceeds 60 centimeter per second. And correspondingly, we can see here from the response spectral, there is very rich content in the moderate to long period range. And this is the design spectral, the local design spectral. You can see the Moxi record has exceeded the design basis level in this period range and almost reached the maximum considered earthquake level in this period range. The other thing I want to mention is the significant vertical component of Moxi record. It's almost the same as the horizontal component in terms of PGA and PGV. Okay, I think we are ready to go into town. Now this is actually what the town of Moxi looked like. It is a tourist town, and the buildings along the street are decorated with this kind of Asian-looking timber structures. And debris show the damaged house, collapsed houses, and most of the debris on the street are actually the decorative timber frame. And most of these structures are timber looking, but actually they are masonry structures built by the owner according to the local rule of thumb. And most of them are not seismically designed by professional engineers. But there are also buildings, masonry structures in that town that is designed by professional institute and conformed to the Chinese seismic code. And here I will show you an example of a building M6 labeled here. This building is an office building belonging to a scientific observation station in the town of Moxi. And you can see from the photo that the first story is completely smashed. And very unfortunately, a graduate student who worked there was killed by the collapse of the building. And this building immediately made the headlines in newspapers and social media. And some structural engineers are interviewed for this damage. And they quite blindly assume that this building is a reinforced concrete frame, but actually it is not true. It is actually a confined masonry. By confined masonry, it looks like this. The unreinforced masonry wall is confined by this kind of cast in place columns and ring beams. And the columns has very small cross sections at the minimum rebars. So they are usually referred to as tie column. And from the photo in the field, we can clearly see that the seemingly RC column is not frame columns, but tie columns. If you went to behind the buildings, it's even clearer to see that all these columns, the reinforced concrete part, are tie columns rather than frame columns. Another rumor about the collapse of this building is that there might have been an open space in the first story. So the building, that's why the building collapsed in such a way. But we are lucky enough to get access to a drawing of the first story of the building. And we can see many walls on the drawing, and the wall ratio, according to the Japanese knowledge, is very high, and is not likely to have a big first story. So, but the drawing is not necessarily the reality, but so the cause of the collapse remains something to be further studied. Another hypothesis for the collapse of the building M6 is located over here, is the effect of terrace. We can see this as a very large terrace called the Moshi Terrace. And according to the geologist in the field, the riser of the terrace is more than 100 meters. And it might have significantly amplified the ground motion of the site. And also on the edge of the Moshi Terrace are two RC frame here. I labeled as F6 and F7. Next, I will introduce some damage to these two RC frame. And they are a Tibetan art museum, so they are decorated to have a Asian Tibetan architecture appearance, feature the very thick stone masonry and all the decorations. But actually behind all of this is a RC frame, two-story RC frame with very regular plan. Now, inside the building, from outside, you see maybe the building seems good, but actually inside the building, all columns sustained very severe damage to both ends like this. And you can see very clear sign of shear failure at the ends. And if you take a closer look, you can find many mistakes in the reinforcement detail. For example, the left slices of the longitudinal bar is too close to the bottom end of the column. And you can also see the hoops only made of diameter 6 millimeter plain bars, and they are not provided with sufficient hook and sufficient bend. Another observation is that you can see very few coarse aggregates in the concrete. So all this evidence makes one worry about the quality of the construction as well as the design of this RC frame. And non-structural damage also caused the problems. This is the typical example in the somewhere away from Moshi, but it's also very close to the epicenter. It is labeled as F8. It is a reinforced concrete frame, and the structure remained intact during earthquake, but the building was tagged yellow to suspend its occupancy by local experts because of the very extensive non-structural damage in the building. In the lower floors, we can see very typical damage to the non-structural masonry infill like this. And in the second and the third floor, we found damage to the cable train hanging over the corridors. And in upper floor, we found more. The wall is okay because of the small deformation of the building, but we found the overturning of many freestanding contents like the cabinet, and you can see the monitor here on the desk, and the overturning of the printers and something like that. And on the top floor, which is the fourth floor, there is a big hole, and the large suspended ceiling, you can see it here, lost more than 80% of its panels. And we also found the broken glasses of the sliding window in that hall. And this kind of non-structural damage didn't impose any safety issue to this building, but because of the suspension of the occupancy, the personnel of the building has to be evacuated to the open ground, and they have to stay in the temporary shelters opposite to the ground. Because of the restoration of the building may take a long time and great effort after the earthquake, because it's the aftermath of the earthquake. And so people there may have to stay outside for several months, I'm afraid. Okay, just now I just quickly go through the typical damaged conventional systems, and then I will focus my attention to the damage of the base isolated buildings in that region. Before that, I'd like to share with you the growth of the number of base isolated buildings in China. And we can see here the first base isolated building in China is constructed in 1993 in Guangzhou, where there's no such earthquake. And before the great earthquake in 2008, the Sichuan earthquake, Professor Peng just mentioned, there are only 100 to 200 base isolated buildings in the entire China. And stimulated by the disaster of the Sichuan earthquake, the government decided to promote the application of new technologies for seismic protection, including base isolation. And many laws and administrative orders were issued. And with that, the number of isolated buildings constructed in the Chinese mainland increased very rapidly. And in the year of 2018, 10 years after the Sichuan earthquake, the number, a conservative estimate is about 6,000. But actually, the true figure, the professionals believe that may have exceeded 10,000 in 2018. And now we believe that China as a whole, because it's a very large country, owns the most base isolated building in the world, even more than Japan. So with this background, it's not surprising to find two base isolated buildings in the epicenter area of the earthquake. And the first one I'd like to introduce is located somewhere here between the town of Moxi and another town of Yanzhou. And it is a magnificent building. It's a main building of a college. And only the central part of the building, as shown here with the pink shading, is isolated, while the surrounding structures, the podiums, the two podiums and the main entrance and the small platform and the back entrance, they are all fixed based. And the main building rests on an isolation layer consisting of lead rubber bearings and natural rubber bearings. I denoted it as the red dot and the white dot. And there are also 12 viscous dampers, 6 in each direction. And as the isolation bearings themselves are okay, they performed very well. And in the field, we cannot find any damage or residual deformation on the bearings. But almost all the viscous dampers sustained damage to a different extent. And this is the typical view of kind of damage. Many of the damper buckled globally like this. And both ends, the connection, the anchor is okay, but it buckled. And this damper buckled here in the threaded connection between the cylinder and the extender. And the other type of damage is in tension. The anchorage of one end of the damper is pulled out, and the damper fell from the RC pier. And there is another type of extraordinary damage that it's buckled in compression, and at the same time, it is the anchorage is pulled out in tension. And in case some of you may not be very familiar with this isolation, I'd like to provide some more information about the details of the isolated building. And you can see here is the rubber bearing. And everything above the rubber bearing is called a superstructure. And the superstructure is separated from the ground with this kind of what we call the isolation gap. And over the gap, there must be some cover plates to prevent people or objects from falling. And according to the drawing, the cover plates should be cast in place together with the superstructure. But the reality is the cover plate, as you can see here, is precast concrete panels, and they are connected to the superstructure through this kind of post-installed anchors. And during the earthquake, the superstructure on the isolated layer must be drifted a lot. And for some reason, the cover plate, the PC panels, didn't move together with the superstructure, but instead the post-installed anchors were pulled out from the superstructure, leaving a large gap between the panels and the superstructure. And this provided us a very important information about how much the isolation layer has deformed during the earthquake. And the in-field observation is about 220 millimeters. And we tried our best to build a numerical model based on what we knew about the building. And under the input of the Moshi record, which is very close to the site, and our estimation is the maximum deformation of the isolation layer is about 204, around 200 millimeters. It is still smaller than the site observation, but we are quite satisfied with this result because there are many uncertainties in the ground motion, and also we didn't know all the information about the building. Another thing I want to comment on is the intensity level of the ground motion. I just mentioned that the Moshi record is featured by near fault pulses, which you can see here from the moderate and long period content. But we estimated that the equivalent period and 100% shear strain of the rubber bearing is about 2.4 seconds for the isolated building. So at this period, the response spectral level is similar or even below the design basis level in the local region. So we can see that the building has experienced the design basis level earthquake in its earthquake. And at such a level, the viscous damper should not have been damaged like this. So maybe the reason for such a damage may be complicated, but there's the obvious one. This is the damping force of a viscous damper. But from the design drawing, we found that according to its alpha and CD value and design force of 700 kilonewton, the corresponding velocity is only 2.4 millimeters per second. That's to say, what the engineer, the designer expected is something over here. This is a very low velocity. But our estimation, our calculations show that the actual relative velocity of the isolation layer is around 800 millimeters per second. So what happened in the earthquake is somewhere here. So here, I bet I really doubt if the engineer understand how a viscous damper behave. Maybe he just assumed that it's something like a metallic damper, and it will yield at the design force and later impose a kind of upper bound for the force, but actually it's not the case. Other damage to the isolation layer is very typical, like this kind of broken pipes because of absence of the flexible joints, and also the collision with the surrounding fixed base structures like the stairs here. Okay, the second isolated building is smaller in scale. There's a 4-story reinforced concrete frame building resting on an isolation layer of only lead rubber bearings of a diameter of 6 millimeters, 600 millimeters, and 700 millimeters. And it is somewhere here. It's right on the town of Moshi, and very close to the strong motion record here. And there's no viscous damper this time, but very surprisingly, we found very extensive damage to the rubber bearing. This is an example. This is a rubber bearing of a diameter of 600 millimeters. It's fractured on top layer like this. And this is another example, the rubber bearing fractured at the bottom layer of the bearing. And again, it is very important to find that the residual gap between the cover panel, which is also PC precast concrete panel, and the superstructure is about 200 millimeter. And again, we built a numerical model and under the Moshi record, but this time it is not aligned with the east-west direction. So we have to rotate the ground motion to match the reality. And this time our estimated maximum deformation of the isolation layer is about 170 millimeter. This is about 15% lower than the 200 millimeter observation in the field. But we are still quite satisfied with this result because of the lack of information of the superstructure. We have to estimate all the information according to the field observation and the relevant code and standards. And again, this time the isolated period is around two seconds. And even if the Moshi record showed very, very clear pulse-like characteristics, but at this period, the response spectral level is still design basis level. The last thing I'd like to comment on is the effect of the vertical component of ground motion. I just mentioned that in Moshi record, the vertical component is very significant. And our analysis showed the vertical ground motion really had a great impact on the vertical stress of the rubber bearings. This is for the compressive stress, this is for the tensile stress, and almost all, except these two rubber bearings, almost all of the rubber bearings are in tension for a short period of time. But if you look closer to the vertical stress and shear strain relationship, we found the maximum tensile stress is still far away from the test result, the criteria based on the test result of qualified bearings. The maximum, in this case, this bearing is somewhere here. It has the tensile stress of 0.78 megapascal. And this tensile stress, the shear strain is less than 100%. And for this bearing is somewhere here. The horizontal shear strain is larger, is 160 or 70%, but the tensile stress, maximum tensile stress is only 0.01 megapascal. They are all very far away from the fracture line. So by this result, we can see the fracture, the actual fracture of these dampers may not be simply attributed to the significant vertical component. There might be some quality issue. And this is a summary of my presentation, and I'd like to skip it for time's sake. Actually, we summarized all of our observations in the field in a rapid report published on the Earthquake Research Advances. And it is an open access journal, and you can download the full text through this DOI. And we also submitted 2 Chinese papers to a Chinese journal. And I'm afraid they're written in Chinese, but in case some of you can read Chinese, you can find all the details of the modeling and the discussion about damage to the 2 isolated buildings. And one of them has already appeared online, and the other one is still under review. And finally, I'd like to thank Professor Pan Yi from Southwest Jiao Tong University and Professor Zhang Ruifu from Tongji University, and professors and my colleagues, Ma Qiang and Lin Sichuan from IEM. And the ground motions used in this study is provided by the China Strong Motion Network Center, and the work is sponsored by NSSC. And okay, here's my presentation. Thanks for your attention.
Thank you very much for a very informative presentation. I believe your work with regard to the base isolation buildings is amazing. That open journal, I assume that's in English. Is that an English publication?
Yeah. Yes, it's English.
You know, I would encourage you, and I'm quite serious, to submit something to our journal, the EERI Earthquake Spectrum. I'm serious. This information is very important because in the United States, we have not observed failures of base isolated buildings. So I might communicate with you to encourage you to do that.
Thank you.
Fascinating work on the base isolated buildings. Now I would like to turn the platform over to Volkan, and he'll pose questions. We are going to run a little bit over, but we need to have, I'm sure we have many questions, and we'll run over for maybe 5, perhaps as much as 10 minutes. Please proceed, Volkan.
Thank you, Bruce. Thank you, Professor Zhu. This was a fantastic presentation. My first question would be, you have shown a time versus base isolated structures. And was that base isolated structure number is cumulative number or buildings in each year?
Cumulative number.
That's the cumulative number. Okay.
Yes.
So another question is, when was this base isolated buildings built in the in your study?
Yeah, it's a great question. Yeah, it's a great question. This one is just built and has not been fully occupied when we visited there. So it's a brand new building. So, but on the other hand, this one is built in 2016. So the rubber bearing at that time is not as good as what we have nowadays.
All right. So another question would be do you have the acceleration records publicly available for other scientists to use?
Yeah, as I mentioned, I get the ground motion from China's Ground Motion Network Center, and there is a policy for the Chinese user. You can apply for that ground motion data for free. But I'm not sure the policy for international users. I will consult my colleagues and come back to you.
I see. So another question would be, what does the public think about the base isolated buildings? Are they aware of it? Are they think they are now safer because the building is base isolated, or this is completely because of the requirement of the code design?
Yeah, the rapid growth of isolated building in China is something different from what happened in Japan. In Japan, people think the isolated building is very good, is superior to compared to conventional structures. So they want to investigate investment in this kind of building. But in China, it's the opposite. China is a big government country, so the quick growth is primarily promoted by the government. So I didn't mention here is what happened during these years. The government issued a lot of administrative orders to require all the newly built schools, hospitals, and emergency response centers to use base isolation or passive control. This is an order. So for the public sector, it is like mandatory to use this kind of technique. And unfortunately, the whole industry seems not ready for this kind of rapid growth. So that is the main problem. I think we found such damage in this kind of isolated buildings.
So in your mind, first of all, do you think that this earthquake caused more damage than expected? Or do you think do you think this earthquake caused more damage than expected?
Yes, I didn't expect such damage in base isolated buildings. And as I just summarized, one is because of the design mistake. The other is because of the poor quality of the rubber bearing. So if they are designed properly and the products are of good quality, I didn't expect this.
I see. So how representative do you think this experience for the rest of China? In other words, we know that these buildings experience such damage because that earthquake occurred there. But what if that earthquake were to move around? Would you see similar experiences, or do you think this area was relatively more prone to earthquakes for one reason or the other?
Yeah, very good question. And unfortunately, I think it's very representative all over China. And actually, to my personal experience, I have never seen a single isolated building in China with proper detailing regarding the piping and the cover plate, the isolation gap. And unless we have an earthquake, we don't know the quality of the rubber bearing, the viscous dampers. So this earthquake is a very good, unique opportunity for us to know more about the quality of the products.
Is that because government essentially orders these base isolators to be used, but maybe they are not requiring proper training or guidance for the practitioners to install them? Is that one of the reasons, or maybe since this is just a requirement, people tend to do this as cheaply as possible?
Yeah, there are some problems with the system of the construction sector in China, and it's complicated. And yes, there are training of the designers, engineers, and the practitioners in this field. But you see that the growth of the number of isolated buildings is very fast.
Yeah.
But the training and the growth of the industry is kind of slow. So there is a mismatch of speed, I think.
So another question would be, you have shown in one of these buildings that has both dampers and the base isolators. Do you think that was, and dampers actually sustained quite a bit buckling. Do you think that was, I guess my question is, as a non-structural engineer, do you think the reason of extensive damage in the dampers is due to the base isolation, or they are unrelated? In other words, because base isolators would allow building to have more displacement. So I wonder if that increased the reason why that caused such damage.
Yeah, it's a good point. But these dampers, these viscous dampers, are especially designed to accommodate the large deformation of this isolation layer. We can see here from the figure, the stroke is as large as 600 millimeters for this damper. This is very slender dampers. This is a problem, but we can do it. Like MPS can have very slender actuators without problem in the test. But yes, your concern is right. The deformation requirement for this kind of dampers are very large because they are installed in the isolation layer. But the problem with this damper is too long. The problem is there is a design mistake in the key parameter, which is the velocity of the damper. So practically, to explain it more clearly for a non-structural engineering background people, it is not like a damper, it's like a brace, because the design velocity is too low. When the velocity exceeds it, the force will go up very quickly like this. So it practically worked as a steel brace, a very slender steel brace. It cannot shrink or extend freely. So it is stuck.
I see. Again, from the outsider's view, other base isolators that I saw had steel plate, rubber, plate, rubber, plate, rubber section. But the ones that you saw damaged, I didn't see steel component in there. Maybe I didn't. Did they?
Yeah. What you see is what you see, the one layer rubber, one layer steel plate is the cutoff view of the damper. In real case, inside there is layered, laminated. But the real rubber bear will have a protective rubber layer to wrap it.
I understand.
Protect the inside the
steel
plate from rust.
So inside would be still the same. I understand. Okay.
Yes.
All right. That's very good. We have a follow-up question saying, what was the loading velocity of the bearings tested in the lab as compared to the working condition under the earthquake? And I think that was a question about the second building.
The second building?
Yes, fracture of the isolators. Yes, the one that created fracture. Yeah.
Oh, I didn't know the specific number of the loading speed. In China, we require all rubber bearings to be tested before delivery, but we didn't require a high-speed test. Quasi-static and some dynamic test, but not that high-speed test. I will check up the number in the code. There are some standards.
Do you anticipate that the experience from this earthquake will create some actions in terms of mitigating potential risk of the other base isolated buildings in China? In other words, okay, now we learned this. Are we going to do anything about it?
Yeah, after the earthquake, when I saw this kind of damage, I'm astonished, and I immediately published it on social media on my something like a blog, and it made a very big effect. And as I know, some local government has already started to check all the base-isolated building in their territory, and this is a good thing because we expose the problem to promote the government and the institutes and designers to pay more attention to the quality and design of the isolated building. I think it will be getting better.
Fantastic. So I cannot thank you enough for this generous dissemination of great information. And we hope that part of our members and people who watch this presentation, they will contact you and potentially find ways to share knowledge and learn from each other to make every place much safer. Thank you so much. And I will give the microphone to Bruce to make final remarks.
Okay, my final remarks are that fascinating presentations. Thank you to both of our presenters. We learned a lot, and we hope you will share more with us, to be quite frank, especially on this base isolated building. Is just fascinating. That's all I have to say. Thank you so much. We enjoyed your presentations. I'd like to turn the control over to Elizabeth for some closing remarks. Elizabeth, please.
Thank you, Bruce. Thank you to our speakers. That was great. I just wanted to ask everyone to please complete the post-webinar survey that you'll receive by email tomorrow. That helps us get feedback on these events and create new ones that better meet the needs of our audience. You can learn more about EERI at our website. And as noted, you can find out about upcoming webinars by joining the mailing list Bruce mentioned or by checking our Pulse newsletter. And then finally, I want to thank both FEMA and EERI members like yourselves for making events like this possible with financial support. Thank you.